Welcome to another new video of interesting math problem on our channel Math Solutions for You. Please do like, share, comment, and don't forget to subscribe to our channel. The lengths of the two shorter sides and hypotenuse of a right-angled triangle are integers a, b, and c respectively, where c minus b is equal to 1. We are given 5 choices and we have to pick all correct options. So this type of multiple choice question is a little bit harder than the run-of-the-mill multiple choice questions because these questions may have more than one correct options, and in order to get credit for these, you have to pick all the options which are correct without including any incorrect option in your pick. So this makes these questions a little bit harder because you have to give careful consideration to each of the options that are presented. We start this problem by writing out the relationship between the lengths of the sides of a right-angled triangle, and that's simply stated as Pythagorean theorem, which states that the squares or the sum of the squares of the two shorter sides of the triangle is equal to the square of the hypotenuse. So a square plus b square is equal to c square. And from that, we basically have a square is equal to c square minus b square. And we can further write c square minus b square as c plus b multiplied by c minus b. And since c minus b is given as 1, then this simply becomes c plus b. So we have a square is equal to c plus b. Now, from the relationship c minus b equal to 1, which is given in the problem, we can write c in terms of b as c equal to 1 plus b. That's very elementary. Now, if we substitute c equal to 1 plus b in the relationship that we obtained earlier, which is a square is equal to c plus b, we basically get a square is equal to 1 plus 2b. And let's just call this equation 1. Now, a square equal to 1 plus 2b implies that a square is odd, because 2b, being a multiple of 2, is an even number, and we know that when 1 is added to any even number, the result is an odd number. So that makes a square odd. And for an integer, for a square of an integer to be an odd number, the integer itself has to be odd, which implies that a must be an odd number. And this has to be always true, right? For these relationships that are given to be true, a has to be always an odd number. So next, if a is odd number, we can write a in this form, 2k plus 1, where k is a positive integer. Because a is odd, we can express a like this. And now, if we substitute a equal to 2k plus 1 in the equation 1, then on the right-hand side, on the left-hand side, we have a square. So a square becomes 2k plus 1 whole square. And the right-hand side is 2b plus 1. So we have 2k plus 1 whole square is equal to 2b plus 1. And if we expand 2k plus 1 whole square, we get 4k square plus 4k plus 1 is equal to 2b plus 1. And from this, it's simple to obtain b is equal to 2k square plus 2k. And if we take 2k common, then we have 2k multiplied by, within parentheses, k plus 1. Now, this term, k multiplied by, within parentheses, k plus 1, that's basically the product of two consecutive integers, and that has to be a multiple of 2. And then we already have a 2 before, right? So taking these two 2's together, b must be a multiple of 2 multiplied by 2 or 4. So we arrive at this conclusion that b must be a multiple of 4. And if b is a multiple of 4, then that makes b an even number, obviously. And then c is basically 1 plus b. So we know that 1 added to any even number must be always an odd number. So c must be always odd. So far we have seen 3 results that seem to be always true. A must be always odd, which is basically, your option D, right? Then B must be a multiple of 4, which is your option B. And C must be always odd. So we have found 3 out of the 5 given options as correct. But we have to verify, whether the other options are correct or not. Mainly option A and option C. So let's do that, but before doing that, I'll clean up here to make some space, but I'll carry over some of the important results. So we have shown that a square is equal to 1 plus 2b, so that was our equation 1. We have concluded that a must be always an odd number. We have also shown that b must be a multiple of 4, and we have concluded that c must be always odd. Now we haven't proven whether options A and C are correct or not. So we haven't shown otherwise that they are incorrect, right? So what's the way to approach that? Well, one way to approach it would be to consider some examples of Pythagorean triplets that satisfy, the conditions that need to be true with A, B, and C. And what are those conditions? Well, first, A needs to be odd. It needs to be an odd integer, right? And then from equation 1, we can express B in terms of A as simply B equal to A square minus 1 whole divided by 2. And then C is simply 1 plus B. So let's start with example of an odd number. The simplest of odd integers, excluding 1, would be the immediately available odd number that I can think about is 3. And if A is 3, then that makes B as 3 square minus 1, which is 9 minus 1, 8 divided by 2, which makes B equal to 4, and that makes C equal to 5. Now, in this particular set of A, B, C, we find that A is divisible by 3 and C is divisible by 5. But that doesn't guarantee that these options would be always true. So we have to basically consider all potential cases and then come to a conclusion. So what do we do? Well, we can at least try out another set, and for that we start with A again. So the odd number that's immediately available after 3 would be 5. So let's set A equal to 5. And if we set A equal to 5, B becomes 25 minus 1. So that's A square minus 1. 25 minus 1 is 24 divided by 2, 12. So B becomes 12 and C becomes 13. So in this example, it's easy to see that A is not divisible by 3 and C, being 13, is not divisible by 5. So we have a contradiction of both the options A and C in this case. So we can conclude that the options A and C will not be always true. So the correct choices for this question would be options B, D, and E.